No, bases are better. Acids are better. No,
Acids, bases. Calm down. These people don't even know what you are yet. Let's start with an introduction.
The scientific world was in a very bad state when nearly 400 long years ago discoveries were made. Wait! Arrhenius was cool, that Gilbert Lewis was a fool, and Brønsted-Lowry was a tool. They used hydroxide and hydronium. Math, science, chemistry, they made discoveries chemically that started with an acid and a base. BANG!
Let's ask ourselves, what are acids and bases?
Hello, my name is Svante Arrhenius. I decree that acids produce hydrogen ions in an aqueous solution, while bases produce hydroxide ions when dissolved in water.
Thank you, Arrhenius. However, his theory is limited to aqueous solutions and only applies to one type of base. Is there another less limiting definition?
Yo, my name is Gilbert Lewis. You may remember me from the Lewis dot structures. That's right, I did multiple science things. And my acids and bases definition is the most general. I say that acids are electron pair acceptors, and bases are electron pair donors. What?
However, the definition of acids and bases most often applied in chemistry is not Lewis's theory. It is the Brønsted-Lowry theory.
Hilsner, my name is Johannes Brønsted-Lowry, and my definition of acids and bases is the best, as proven by the fact that you will be using my theory all unit. And of course, my definition states that acids are proton donors, whereas bases are proton acceptors. Yay, Brønsted-Lowry! Hey, acid, back off! You're much too sour to be able to love Brønsted-Lowry like I do. No way, you're just bitter! Ha!
Quiet, children. You're both right. But stop this argument. Getting back to the definition of acids and bases, in a chemical reaction, acids lose a hydrogen atom and bases gain a hydrogen atom. Take a look at this chemical equation. Take the chemical equation, HClO4 plus H2O yields H3O plus ClO4 minus. In this equation, the reactant HClO4 loses a hydrogen to turn into ClO4 minus. Therefore, HClO4 is an acid. The reactant H2O, water, gains a proton to turn into H3O plus. Therefore, in this equation, water is a base. However, water is not always a base. In fact, water is known as an amphoteric compound. This means that water can act as an acid or a base depending on the reaction.
Yay, I'm special!
Yes, water, you are special. Another special compound is H3O+, also known as hydronium. Hydronium is formed by adding a hydrogen to water. So if I'm a base in this equation, what do you call hydronium? Great question, water. Now let's introduce conjugate acids and bases. In this equation, since you are a base, hydronium is known as your conjugate acid. In chemical equations, acids turn into conjugate bases, and bases turn into conjugate acids. So if HClO4 is an acid, what is ClO4 minus?
I'm a conjugate base.
Right.
So what does all this mean?
Well, kids, there's a magical color system that we call the pH scale.
Yay!
At one end of the pH scale, we have acids. Acids have lower pH values than bases, and they range from 0 to 6. On the other side, we have bases, which have higher pH values. Bases range from 8 to 14. And in the middle, we have a magical neutral spot at 7. This, kids, is where you place water on the pH scale. Yay, me!
But what does pH really mean?
Well, pH measures the hydrogen concentration of a substance. Acids have more hydrogen ions than bases, and bases have more hydroxide ions than acids. Therefore, from 0 to 6 on the pH scale, more hydrogen atoms are found. But what about me? Good question, water. When we mix a strong acid with a strong base, the substance neutralizes. The product has a pH that is closer to 7, just like water. If we mix weak acids and weak bases, the same thing happens. But if we mix a strong acid with a weak base, what do you think will happen?
It's more acidic. Ha!
Alternatively, if we mix a strong base with a weak acid,
It's more basic. Na na boo boo.
this type of reaction is called a neutralization reaction. The products of a neutralization reaction are a salt, or an ionic compound, and water. Yay! But how do I know if something's an acid or a base without sock puppets?
We're not sock puppets, we're real.
Sure you are, kids. An indicator is a device that changes color depending on the specific pH value of the substance to which it is exposed. Litmus paper is a classic example of an indicator. It turns red when exposed to an acid.
Yay, that's why I'm reddish.
It sure is, kiddo. And it turns blue when exposed to a base.
Yay, I'm sort of blue.
Anyway, you use an indicator when titrating a substance.
How does that work?
I'm only vaguely glad you asked. If you take a look at this excellent visual.
As you can see, the burette contains a set amount of an acidic substance. Meanwhile, the flask contains a base and an indicator. When equal moles of hydrogen and hydroxide are mixed, the indicator changes color and the pH is neutral.
Yay! So are we done yet? This is boring.
Trust me, kids, I'm only here because they're paying me. Anyway, look at these flowers.
Holy guacamole, we're outside! Yes, an astute observation, kids. Now, if you look at these flowers, you will see that in acidic soil they turn blue, and in basic soil they're pink.
Another example of an indicator! Yay! But why is only one flower pink?
Because the gardener here screwed up.
Yay!
I'm going to take a nap now. Bye, everybody.
Yay, it's over!